Okay. So what we did, I discussed large class, started with this concept of decision theory. So only decision theory I have explained, and that what is Bayes rule and how Bayes rule helps us to make a decision of classification. So that is what I had explained. From here, how do we use decision theory? When we are trying to solve this classification problem, we can break down this problem into two stages, inference and the decision. We use training data to make inference. That means we learn from the training data, build a model, and use that model to make certain decision. Say, for example, when we have a say probability, this is a posterior probability that we can find out using Bayes rule. One of the ways of finding out this posterior probability is the Bayes rule. So if we get this probability, say probability of anybody having a disease, say 0.7. So whether we should classify this as a person is having a disease or not having a disease. So that is what is a decision rule, and you have to make a decision on that. So there are algorithm which gives the output in the form of the probabilities. So that's what probabilistic interpretation helps us in finding of the inference, and then we have to make a decision based on that. Now we have a different kind of classification models. One which relies on these probabilities. So we get output in the form of some of them gives the output in the form of a probabilities, and then we convert this probability into either 1 or 0. I'll take example of classification, binary classifications. We have two class problem. One class is class 1, one other class is class 0. So we call it 1 and 0. In that we have generative models, discriminative models, and then second type of model, a discriminant function, which has nothing to do with the probabilities. What are the generative models? Say, for example, there are algorithms which gives us the posterior probability, like Gaussian, naive-Bayes, mixture of multinomials, mixture of Gaussians, Bayesian networks. These all are the algorithm which gives us the posterior probability. In your syllabus, we will cover naive-Bayes as well as mixture of Gaussians. Say, naive-Bayes uses the Bayes algorithm plus certain additional features, some modification to the Bayes, or I can say some assumptions, but it uses this Bayes rule, which gives us a posterior probability. So how do we interpret this probability that we get in terms of a probability distributions? Now, can someone tell me what is a C over here? Yes?
An event.
No, now I want the answer in terms of machine learning. It's anyway mentioned here also.
Class.
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 So what are we doing? Given the given features, what is the class? For each class, we are finding a posterior probability. So with a very simple example here, with when we have x1 and x2 two features, and then we are drawing all the data points. And you can say blue data points belongs to one class, and red data points belongs to say another class. Say I can say this is a class 1, and maybe this is a class 0. So here it's mentioned cross is class 1 and zeros are class 0. And what we get is the probability distribution for each class. So you can say this red region and the blue region. Any data points within this region, say for example, blue region, will be classified as class 1. So our generative algorithms gives us the probability distributions per class. So even if we have just 4 data points currently, we can generate additional data points by knowing the class distribution, class probability distribution. So in this example, in the blue region, we have just 4 data points, but I can generate because now we have defined this class distribution, so new data points can be generated. That's the reason the name is generative models, and it exclusively gives us the posterior probabilities. And how does it calculate this posterior probability? using this formula. Now that's important to understand this formula, like from probability or mathematics point of view, they are just the formula. But what is happening here? First, we need to find the likelihood. So this is a conditional probability of X. That means features, condition on the class for each class. We call it as a likelihood. More on likelihood when we will study again post mid semester this concept in detail. But say for each class, we need to find out this conditional probability. We have so many features. Then for each class, we have to find the class prior probability. We find this two independently for all the features, all the examples. And after this, then we plug in those values in this formula, we get this posterior probability. How many probabilities we need to create, we need to calculate or compute in order to find this posterior probability. So that is one of the drawbacks. So many computations are required just to find this probability. We use that, then we use this probability to make a decision, whether it's a class 0 or a class 1. So that's the generative models. And generally, whenever we have a high dimensionality, then with so many features, then we generally need a very large training data sets. Now, another kind of classification is a discriminative classification, which says that algorithms which can gives us the boundary. We call it decision boundary. So the decision boundary, that means it can discriminate between the class 0 and class 1 by the use of this decision boundary, whether it's a linearly separable or non-linearly separable. So when we have a non-linearly separable data, say for example, something like this. In that case, we'll get a class boundary like this. So the algorithms which output such class boundaries, they are known as discriminative algorithm. A very specific case of a discriminative algorithm is a logistic regression, where we get output in terms of this posterior probability. But we are not calculating any likelihood or a prior and applying a Bayes rule. No, we are not doing that, but we are getting output in the terms of a posterior probability. So that's what will happen in logistic regression, and that's what I'll discuss today once I'll complete this theory. The other classifier like SVM, decision tree, nearest neighbor, neural network, etc., are also discriminative classifiers because they give us a decision boundary. So any algorithm which can give us a decision boundary, which can discriminate between class 1 and class 0, they all fall under this discriminative classifiers. So when I want to compare between this generative and discriminative, with a generative classifier, we can actually generate data points. So say when we have this spam classification problem, spam email, non-spam email. So whatever discriminative classifier will actually work or will give us, it uses a training data set. What will be there in a training data set? There will be spam emails and non-spam emails, which are a labeled data set. So manually somebody has labeled, this is a spam email, this is a non-spam email. And then from those emails, some features are constructed. And then some kind of feature engineering will happen and we'll get very structured data in the form of rows and columns. And then we can use this kind of, say, logistic regression algorithm or any other discriminative algorithm, which will give us a kind of a decision boundary. And then we have to identify which side of this decision boundary any new unseen data points belong to. So when we say any unseen data points over here, this is unseen because it falls on the lower side of decision boundary, where rest of the data points have been labeled as a 0, class blue. Then this unseen new data point will also be labeled as a class 0. It's a discriminative approach. So when new email comes, depending upon on which side of a decision boundary it will fall, it will be classified as spam or non-spam. Then we have a generative classifier where this is something like in a feature space. How does this spam email looks like, and how does this non-spam email look like? So say for example, if I take a cat and dog example, how the cat looks like and how the dog looks like. So that will be learned by the model. And then when the new unseen data points, unseen picture will come, model will be able to distinguish between it is cat or dog. So this is just trying to understand and with a real example, how does generative works and how does discriminative works. One more example here to differentiate between discriminative and generative model. Say we have a handwritten digit classification problem where we want to identify digit 0 and digit 1. This is the left side. We have a discriminative model, probability of y by x. This is what we will find directly. Posterior probability we will find directly. And when we have a generative model, we need to find likelihood, then prior, and then we'll find the posterior probability. Now you can see each of the data points are labeled. The first two are 0, the next two are 1. So this way a model will learn this is a decision boundary. Above this decision boundary, there are zeros, class 0, and below the decision boundary, there will be class 1. So this is a decision boundary which will be learned based on the training example. Here we have just four training examples. So based on these 4 training examples, this simple decision boundary is learned. But in case of a generative model, a probability distribution would be learned for each class. So this is the distribution curve for the class 0, and this is the distribution curve for the class 1. And then any data point coming within that distribution will be labeled as either class 0 or a class 1. So again, this is another way of discriminating between generative and the discriminative models.
One
Yeah.
question. So in case of discriminative model, there can also be multiple decision boundaries if there are multiple classes more than 2.
Yeah, I will also discuss about multiple class. How certain algorithm handles multi-class problems. So that we will learn with respect to first logistic regression, how the logistic regression handles multi-class problem. It varies from algorithm to algorithm. So when we have a multi-class problem, what kind of activation function we are using? So sorry, what kind of hypothesis function we are using? So it is different. Neural network learns multi-class in a different way. Decision tree gives us multiple decision boundary.
In principle, let's say
Yes.
instead of 2, we
Yes.
have multiple classes, then there will be multiple decision boundaries.
Decision boundary, yes, yes. Okay, yeah.
I'm trying to understand the difference between generative and the discriminative models. So in this case, how are they different? See, in both the cases, I see that in discriminative model, there is a north and south, or up above the decision boundary and below the decision boundary. And in generative model, I see a very defined boundary for y equal to 0 and y equal to 1. But otherwise, like what are we generating in the generative model?
First of all, this is a decision boundary in discriminative model. And what you see over here, it is not a decision boundary, but it is the probability distribution. That's what we are learning. Now, what is a probability distribution? There are two. See, this is a very simple example of 2 data points. So from 2 data points, whatever value it is taking, from based on that, we are learning this probability distribution.
Okay.
Okay, so within those probability distribution, if there are more data points. See,
okay, so even if the data points in generative model, maybe the boundary is bigger, right?
Not bigger. It is not related with bigger or smaller. This distribution is been generated, is being I can say identified based on what we have in the training data. Based on that, this distribution have been identified, and within that we can generate few more data points. So that's why it is a generative model. See, I had explained this last class. I don't know whether you were there or not. This is an example to understand what is a probability distribution.
Right.
Okay, this is example curve, a normal curve. Not necessarily every time your distribution curve will be a normal curve. It can take any shape. So the circle was shown just to make you understand. Circle is not always like, distribution.
Okay, so in that case, how will we differentiate whether something is a generative model or a discriminative?
Yeah. So what is the model's hypothesis function? What model outputs? So we'll see in case of like logistic. This is just a general theory. Now you have to understand this from the every algorithm, whether it's generative or discriminative. So that we'll see. In case of generative model, is a naive Bayes algorithm, which gives us the posterior probability. It uses a Bayes rule. So any algorithm which uses the Bayes rule, they are generative model because it gives us a posterior probability. But 1 minute, any algorithm which can differentiate, which can actually gives us a decision boundary in any form, then those algorithms are the discriminative model, whether it's a linear boundary, as I said, non-linear boundary. This is a non-linear boundary. Circle is a non-linear.
Also, there is a decision boundary, right?
Where?
There is a differentiation between y.
There is a differentiation. There is not a decision boundary. That's what. See, decision boundary is a technical term which is used in machine learning, which is used to make a decision. Whether anything below that threshold is the one class, above that threshold is another class. This is actually not a decision boundary. We don't call it as a decision boundary. You may interpret as a decision boundary, that's a different case. So this we call it, it's a data distribution, it's a class distribution, class probability distribution for y equal to 0 and y equal to 1. So it's a jargon, technical jargon. So use a decision boundary only in case of a discriminative model. Or, or the algorithm which like discriminate function also gives us a decision boundary. So algorithm which can, you have to make a decision above something less than 0, something less than if then else kind of algorithms, they do not fall under this category.
But if it is falling within that class boundary, then we say that yes, it is y is equal to 0. Otherwise, if it is falling within that class boundary, then we say it is y equal to 1. Right?
Yes,
so
yes.
either way, there is a
when I want to use a technical term. This is the class distribution is learned, used based on the training data. So for you, me, or for a common layman's language to understand, it's okay, you can call it within the class boundary. But the boundary is not learned by the model. It's a class probability distribution is learned by the model.
Got it. Okay, ma'am.
Ma'am, how about clustering algorithm? Which category does that fall under?
It is unsupervised algorithm. So these are the types of only supervised classification algorithm. Clustering is unsupervised, so it is not used for classification purpose.
Oh, okay, yeah, got it.
Okay, the third category is discriminant function, where we are not learning any posterior probabilities, but there are some class of functions known as the discriminant functions. They are used. There are different discriminant functions like quadratic discriminant function. Here I have shown example of linear discriminant function. Then there is Fisher's discriminant function. There are many more discriminant functions. One or two are explained in Bishop, but just so that you to give you the awareness about this. Say we have a linear discriminant function. This is example of a linear discriminant function. Then based on this, some decision rule is used. If the value of this discriminant function is greater than or equal to 0, then it is 1, otherwise it is minus 1. So this is the threshold is fixed to 0. Mathematically, we can write this, we can combine these two equations using this sine function. So this function directly gives us output in the form of whether 1 or minus 1. This is, so sine function is linear discriminant function. Sine is a sine function. So whatever value will be evaluated inside a sine function, we will pick up its sign. It's a positive sign or a negative sign. So that will give us the class 1 and class 0. That's the decision function where we are not getting a posterior probability or how are we learning this parameter learning? Ultimately, these W's we have to learn. So there are method of least square method, perceptron algorithm. You will learn this perceptron algorithm in deep learning. It's a base for the neural network. Then Fisher's linear discriminant. So all are these different types where these parameters are learned. Just we are not going in detail of this discriminant function, but for the sake of completion, what are the different classification algorithm, like different algorithm falls under which categories? This is what we am explaining theoretically here. Now we'll again focus back on the classification. First of all, how we can we solve the classification problem using regression? Okay, say we can use a discriminant function, linear discriminant function. You have seen this hypothesis function before. Where have you seen this? Yes, which algorithm?
Linear regression.
Linear regression. Yeah, so a similar kind of. Here we are using this and decision rule. Our decision boundary will be given by this function, and then if the value of this function is greater than 0, greater than or equal to 0, the class will be 1, otherwise class will be -1. So based on that, we can define some decision boundary, and then above and below, we can have some class. So this is one way of using a regression kind of a function for a classification task. Then we have a linear regression. The other name of linear regression is the least square regression. Why do we call it least square regression? Because we are using the sum of square or mean square error as the error function, and we try to minimize it during the training. So we want to use the least square regression, least square error. This is just some plot done using some sample experimental data points. Blue line is linear regression, and the green line is the logistic regression. Now we have data points using both this function. I will explain what is logistic regression. I'll start next, but you know what is a least square regression hypothesis function. This we have come up with this decision boundary. Please mute yourself. Someone is unmuted. Now, what happens if we add some different, some additional data points? So you can say some blue data points have been added. And if we use a linear regression hypothesis function to classify these 2 points, our decision boundary changes. And it is tilted more towards the new additional data points that we are added. So least square regression uses the least square error. It tries to minimize the sum of square error. So whatever additional data points adds to that error function, and then the decision boundary changes. But with a logistic regression, addition of this data point doesn't change its decision boundary. For this specific case we are telling, it's not like every time it happens. Just for a comparison, we have taken this additional blue data points which are added, which are actually outliers. You can see that the rest, all the data points are within some range. And there are only few data points which have been labeled as the class blue, which are actually very far. So I can call them as outliers. And this outliers, because of this outliers, decision boundary of linear regression changes if we use a linear regression hypothesis function, but it doesn't affect the logistic regression hypothesis function. So these are the reasons. This is one of the reasons that we do not use a least square objective function to implement the classification problem. But we use something called a logistic regression is one of the algorithm. Like we are comparing between these two, and which has got a different error function than mean square error.
Ma'am,
Yeah.
one question. So, in the very beginning of the sessions, we learned that regression models are those which basically predict numbers, and then there are classification models which perform classifications. Here we are using a regression model for classification. Are we mixing things up here?
Here, this slide.
Yes, logistic
Yeah.
regression we are using for classification, but regression models are to predict some numbers, right?
Okay. So that is what I'll explain. Regression is just a name which is added and why it is added. One is a regression name, absolute name. The one is a regression technique. Here, the regression word is used as an absolute name, not a technique.
Okay, it's not a category. Okay.
No, no. And why I'll explain that, why it is used. Okay, so this is a logistic regression, another second algorithm. I can say first algorithm that you will be learning for the classification purpose. It is also known as the generalized linear model. It's under the category of generalized linear model because we are still linear in parameters. What is the hypothesis function? This is the hypothesis function. Sigmoid function. Sigmoid is one mathematical function which is applied to the linear function of data. So this is the linear function of data which we are passing through. So we are transforming this function to another non-linear transformation, which is a sigmoid function. And how do we define? It's a mathematical function. Like we have a log function, exponential function, we have a sigmoid function. So this is defined as 1 upon 1 plus e raised to minus z. This is sigmoid function. And what is a z over here? Z is nothing but W transpose X. Let's say W0 you have added in the W itself. This is the hypothesis function for logistic regression. And suppose we plot Z, which is an input. Here, this is a Z, versus Y, which is a class. We get a curve, S-shaped curved. Sigmoid curve, sigmoid functions are those functions which outputs a S-shaped curved. And what other thing you notice in this in terms of the scale? The output scale. This is output. This is input to the sigmoid function.
0 to 1.
0 to 1. So indirectly, what are we getting output in the form of? Yes,
Probably.
0 and 1.
probability, right?
Yes.
Probability.
So we are getting output in terms of a probability. The other thing, what is this Z over here? It is the it is the linear combination of input. It is what? It's a weighted linear sum of all the inputs. I can say that every feature we are multiplying by corresponding weight. So this is what? W0 x0 plus W1 x1 plus W2 x2 and so on. This is nothing but W transpose X. We write in a vectorized form. So it is W transpose X, which is nothing but summation of Wi xi, where I is equal to 0 to n. N is 0 to say D. So D are the number of features. So this is what. So will this give any number, or it will be confined to between 0 and 1? It can give any number, any positive number, any negative number, right? Basically, a very big number, which will be like we get using this W transpose X, will be squeezed. It will be squeezed between 0 and 1 using this sigmoid function. So we can say we are using this W transpose X, which we are passing through another function, which is a sigmoid function, and we are squeezing its values between 0 and 1. And that's what exactly we want. The output we are getting in the form of a probability. And then we have to define a threshold, which can classify this probability into class 1 or class 0. I can also call output is a smooth function of inputs and the weights. But this is the hypothesis function. And how do we use this function to make a decision? So that's what I'll show you here. But before that, what is this logistic? Sometimes this sigmoid function is also known as a logistic function. So it's a family of functions, logistic family of functions, I can say. And then one of the function is sigmoid. In neural network, when you will learn deep neural network next semester, you will see a lot of other functions which also comes under this category. We have a 10H function. So they are a different formula. Mathematical formulas are different, but they all come under the same category. So here sigmoid function gives us the S-shaped curve. And why are we using this function? It is differential at any point. A function, say this is a function, which at any point we can take and we can draw the tangent and we can find its derivative. And why we need this? We need this kind of phenomena so that to learn the model parameters, we can use a gradient descent learning. The sigmoid function is used for a logistic regression. Logistic are the families of function It uses a sigmoid function, which is a family of a logistic functions. So the name logistic and regression. Why the regression? Because we are anyway taking a weight vector with observation. So we are taking this weighted sum of all the inputs. So that's a regression technique that we are passing through a non-linear transformation. So G is a generally we use a letter to show it's a non-linear transformation. But in case of a logistic regression, we can write a very specific symbol. This is a symbol for a sigmoid function. Like alpha, beta, and alpha function, beta function, we have a sigmoid function. So it's a symbol for a sigmoid function. And G is a general symbol for any kind of non-linear function. So do not get confused between why sometimes there is a G, sometimes there is a sigmoid symbol. Sigmoid is a very specific function when we write, but you can also write a G, a general. So any hypothesis function, lot of like if you will see in a linear network, we write G because there are many such hypothesis functions are there, which take this weighted combination of input and then transforms it. We need a non-linear transformation. So that's how it is used. The symbols and the jargons, they are used like that. So how do we use this? How do we interpret this output? The hypothesis function is weighted sum of input which is passed through a nonlinear function. In the case of logistic regression, that nonlinear function is a sigmoid function. So what is a sigmoid function? How the mathematical it is defined? 1 upon 1 plus e raised to minus z, and z is nothing but the weighted sum of the inputs. So how do we interpret this hypothesis function? We have to interpret in terms of probability, because this is a number we'll get between 0 and 1. Whatever is the output of our hypothesis function will always lie between 0 and 1. So we have to have a probabilistic interpretation for this. So whatever is the value of the hypothesis function, it is actually giving us the positive class probability. Let's say consider class 1 as a positive class. So class 1 probability is been given by whatever value we get after calculating this hypothesis function, and 1 minus that value will be interpreted as the 0 class probability. This is the interpretation of the hypothesis output. Now we got a probabilistic interpretation. So say for example, if you are getting this hypothesis function, say it is outputting 0.6 probability. So what is this 0.6 probability? This 0.6 probability is a posterior probability of class 1. Then what is the probability of class 0? That will be 0.4. This is the interpretation. Now we have to make a decision. So we can say that if y equal to 1 for logistic regression, we use a 0.5 as a threshold. You can see in this y 0.5 is a threshold. The curve changes. It goes from the it changes like at 0.5, it is going from the negative features input space to the positive input space. So at 0.5, we can say it is changing the quadrant on the x-axis. So 0.5 is taken as the threshold point. This is how the sigmoid function works. At 0.5, it changes the quadrant of the input. So this is the input. And at the output of 0.5, it is going from the negative input space to the positive input space. So we take 0.5 as a threshold. So if our hypothesis function outputs anything greater than 0.5, it will be classified as 1. Less than 0.5, it will be classified as 0. Now, what is hypothesis function? It is 1 upon 1 plus e raised to minus w transpose x. If this is greater than or equal to 0.5, then class is 1. So now if you can do a simple math, what we will get, a w transpose x should be greater than or equal to 0. In that case, your class will be 1. You can, graphically also you can see over here, when your input is greater than 0, the input space when it is greater than 0, equal to or greater than 0, then our output is going to be greater than 0.5. Or mathematically also, you can just rearrange this, you will get this equation. W transpose X should be greater than or equal to 0. So Z, which is the input over here, which is nothing but W transpose X, and X are the features, W's are the parameters. So if this weighted combination of input is greater than or equal to 0, then the class is 1, otherwise the class is 0. Our sigmoid function is a nonlinear function. You can see this is a sigmoid function of the input. It's a nonlinear function, but our decision boundary is actually determined by this W transpose X, where this is a linear function. W transpose X is nothing but Wi Xi. And you are summing all of them together. So it's a linear function. That's why we call it as this is a linear classifier, while logistic regression is a linear classifier. So this is the reason. The decision boundary is being determined by this weighted combination of input Wi Xi, W0 X0 plus W1 X1, and so on. So this weighted combination, weighted summation of input should be greater than or equal to 0. Then you will say it's a that particular data point will be classified as 1. This is a linear function, so we call this as a linear classifier. This is just an example how you can interpret the hypothesis output. Say we have an example, just one feature, tumor size. And X0 is the bias coefficient, so which is always 1. If I were to write the hypothesis function for this very simple example, so how can I write hypothesis function here? HW of X equal to 1 upon 1 plus e raised to I will have, say, W0 plus W1 into tumor size. We have just one feature, tumor size, and the coefficient of the bias term is always 1. This is how we can write the hypothesis function. And say, suppose this hypothesis function is giving you output 0.7. So it is greater than 0.5. So this will be classified as 1. The person is having the tumor. But along with that, we are also getting a probability that 70% chance that a person is having the tumor. This is how you can interpret the hypothesis output for a prediction or decision making.
Ma'am,
Yeah.
just one question on the previous slide actually.
Ah.
Yeah. Ultimately, what we see is like this Z is deciding, which is actually coming under zero, it's lying between 0 and 1, and this is what is actually making a decision, right?
One minute,
So
one minute.
Sorry.
Z is not lying between 0 and 1. Z is what? Z is just W transpose X, which is a real number. It could be any high number. Z,
Okay.
we are passing through a sigmoid function, which is giving us output between 0 and 1.
Okay, because we are okay 1 by that value, that is why it's actually coming between 1 and 0. Is that
Yes.
correct understanding?
Yes. Yes.
Okay.
Okay. So decision boundary. Say we have our this is a function Z. We have two features, x1, x2, and then a bias term. And say we are putting some of this W's like this, W0 minus 3, W1 1, W2 1. Just assuming randomly some number, and then we are putting up the number and generating the equation. So what is the decision boundary? It says that this is a decision boundary of logistic regression. W transpose X should be greater than or equal to 0 for Y is equal to 1. And with this hypothetical example, I'm getting equation W transpose X. That means this is a W transpose X. Substitute the value of W0, W1, and W2 in the same equation. So I'm getting this equation x1 plus x2 is greater than or equal to 3. So I will draw a line by x1 plus x2. By looking at the equation, can you say it's a linear function or a linear decision boundary or a non-linear decision boundary? Is it a line? X1
Yeah,
plus
line,
x2.
ma'am.
Yeah, it's a line
It's a line.
passing through 3 by 3.
Yes. So this
3
is
by
how we will get this decision boundary. So above this is class 1 and below this is class 0. This how, so our hypothesis function will be able to give us it's a linear boundary or a non-linear boundary. Now say we have another function. We are defining features like this x1, x2, and then we are taking x1 square, x2 square. We have two features and we're creating more features. And you can say we have taken a square. That means now this function is a non-linear function. You can clearly see this is a non-linear function. It's a quadratic function. And then we are substituting all of these values of weights, just some random values. And we are getting, by substituting, I'm getting this simple equation. So I will add x1 square plus x2 square greater than or equal to 1. Can somebody, I mean, if you remember anything in geometry?
Parabola, I think.
Circle, I guess.
Circle, correct. This is a decision boundary, which is a circular in nature and which exactly passes through this 1, 1, minus 1, minus 1. So this way we can have very complicated function, linear function inside a sigmoid function, and we can get any such different curves. Any such non-linear boundary can be generated using a decision boundary. Logistic regression uses W transpose X, which is a linear. But if I want to, now we have seen what are the linear basis function. I can change the basis function and come up with such a non-linear functions. And then we can use it for the non-linear decision boundary. The same concept which you have learned in linear regression. The linear regression itself is a linear, can classify, it's a linear, it can pass through a linear data points. Similarly, a logistic regression can only discriminate between the linear data points. But what if you have a non-linear data points and you want to use a logistic regression, then we can change this basis function and we can achieve the non-linear boundaries. So another, you can see that the basis function is a concept which can be used at many places to realize the non-linear, to fit the non-linear data sets.
But ma'am, how do we decide these basis functions? Like, is there any guideline for that, or we have to hit and try?
It is like that, hit and try, because see, in a two-dimensional space, you can actually easily plot the data sets and you can see, okay, what kind of a decision boundary. But then in multi-dimensional data space, you cannot plot it, so you will not come to know. So it's simple hit and try. Just like, see, you can say this is another model. This is another model. Logistic integration is another model. Neural network is another model. See, nowadays it's a different case that we have non-linear models as well. So we don't use this logistic regression with a basis function. Neural network gives us a non-linear boundary. Decision tree also gives us a non-linear boundary. So not needed, but anyone wants to, just so this is a mathematical theoretical principle. So even if you have to see those ready APIs has got any support of this basis function or not, we have to check that. But the concept of basis function, how the linear classifiers or the linear regression can be used to fit the data which is non-linear. See, I can use neural network, but the neural network has got a limitation. My data set size is very small. Neural network will overfit the data set. Then you may want to go back and check, okay, can I use a logistic regression? It's a good algorithm. But my data set is non-linear, non-linearly separable. Okay, let's try some basis function. So all this knowledge will help you see, if we use any high level, very abstract level, superficial understanding, we use, okay, at Skillern, we have got different model, choose, try with all the models and see the result, but you will not come to know. Hello?
Okay.
Is anyone? You will not come to know why this result is coming like this. Okay, neural network is good for non-linear data point, but then it's overfitting. It is training error is 0, but the test error is very high. What is happening? You will not come to know because it is overfitting. Your data set size is very small, maybe 1,000 or 5,000 data points.
Okay.
That's why all this inner working, what are the pros, what are the cons? Otherwise, why do we need so many different algorithms? There are always pros and cons of every algorithms.
Yeah.
Okay, so now you have understood what is the logistic regression hypothesis function. Now, what is the next thing? Whenever you understand any algorithm's hypothesis function, what is the next thing that we need to learn? Yes.
How to test it?
Test comes later. We can use this hypothesis function for testing. Hypothesis function is actually used for prediction only, whether testing or prediction. Yeah, but
Training
this is
a model.
training the model. So here, what is the unknown? You see this function, very simple function. Okay, you combine this two. What is unknown over here? X, you know, E is an exponential function. What is unknown here, which you don't know?
Sigmoid.
Slope.
This is a sigmoid.
Weight,
Slope.
weight.
Weights, yeah.
Weights,
See,
yeah.
mathematically, you see, this is my function. This is my function, okay? Say, take example of tumor size. Tumor size is given to us. Okay, this is the hypothesis function, which uses a sigmoid function. What is unknown here? Everything else we know. We don't know what is W1 and W0 and W1 here. So weights, parameters that we don't know with every model. Once you know hypothesis function, there are parameters. It will involve the parameters, weights or parameters. So you have to learn the parameters. Randomly here in this example, I've taken randomly few numbers. We don't know those numbers are correct or not. Here, so what we do, and the next thing you need to learn, how do we learn the model parameters? Or a model weights, chalo, whatever like we can call it, model weights or model parameters. So we have been given a training set, input features, and the corresponding label. And here this is first example, second example. Likewise, M training example, M examples for the training. Okay, and then we have N features. So here N features. For each training example, we have N features. The class is 0 and 1. So this will tell you it is a binary classification problem. And our bias coefficient is always 1. And then this is a hypothesis function. So here the unknowns are these thetas, the feature weights. How do we learn it? Okay, let's say that we use this mean square error. What we use in case of what we have used in case of linear regression. The cost function of linear regression is 1 by m, m as a training example. Like we are iterating through all the training examples. And what is this function? This is
Means
Mean square error.
mean square error. This is predicted minus actual. The actual value minus predicted value, we are taking square. So this is a mean square error. Now, suppose if we take this mean square error, in case of linear regression, we get a convex curve. Like when we do this theta versus g of theta. But when we take we use the same for the logistic regression, we will get this non-convex curve. Why? For a linear regression.
0 to 1 values. So that's
For linear regression, it is simple linear function, theta transpose x, hypothesis function. Because this our cost function involves the hypothesis function, right? In case of logistic regression, it is a non-linear function. 1 upon 1 plus e raised to minus theta transpose x. So our hypothesis function is a non-linear in nature, so we will get this many non-convex feature. So we'll not use this mean square error as the function in the as a cost function, but we will use something called a cross entropy cost function. All binary classification problem uses a cross entropy function. So not just not just logistic regression. You will see neural network also when we use the binary for a binary classification, it will uses binary cross entropy or sometimes just known as a cross entropy. And when we have a multi-class problem, it uses categorical cross entropy. So just let's not go into categorical cross entropy. Here what we will use is a cross entropy function for a binary classification problem. So what is that function? This is how we are defining a cost function. For a class 1, it is minus log of hypothesis function. For a class 0, it is minus log of 1 minus hypothesis function. If you remember in the beginning, this is how we have defined h of theta x. What is the interpretation of h of theta x? It's a probability of a class 1 given input features. And 1 minus h of theta x is nothing but a probability of a class 0 given input features. So that interpretation is used to define this cost function. So for class 0, it is minus log of 1 minus h of theta x. And for a positive class, it is minus log of h of theta x. And I'll combine this two equation in one and we'll get one very nice cross entropy cost function. Let's understand this cost function first for a y equal to 1. So when the actual y is 1, this is the actual value. And you can see when actual is 1 and when the h of theta x is a predicted value. When it approaches 1, the cost is becoming almost 0. So you can say that when actual is 1 and the hypothesis, like your model also is outputting, predicting 1, then the cost is 0. But if the hypothesis, like model is approaching 0, your model is outputting 0, you can say the model is outputting 0 here. The cost approaches infinity. So this cost function interprets that whenever actuals are 1, the actual label is 1, but the predicted label is coming out to be 0, and our hypothesis function is actually predicting the class 1 probability. In that case, the cost is going to be very high, infinity theoretically. Now the same thing we will interpret for the class 0. If the actual is class 0 and predicted is also class 0, you can say here the predicted is class 0 and the actual is class 0. In that case, the cost is going to be 0. And if you can say the predicted becomes 1, but the actual is 0. The actual label is 0. The cost will become infinity. This is what we wanted. In the cost function, this behavior we wanted. So our cross entropy function is giving us that behavior, and this way of writing equation is very difficult to we cannot differentiate. We have to use a gradient descent algorithm where I want to combine this two for class 1 and class 0. So we can combine this class 1 and class 0 equation into one single equation, which it looks very complicated, but it is very easy to understand. The y of I into h of theta. So this is, you can say, actual into log of predicted. This is 1 minus actual into log of 1 minus predicted value. So what we have done over here, this two equation, we have combined. How have we combined? By introducing a variable y. So say when y is equal to 1, what will this equation look like? Forget about all the training examples. So let's simplify for one example. The label, the actual label. So this is the actual label is 1. So you can say 1 into log of whatever we have, whatever is a predicted value, plus what will be here?
0.
0. So we got this.
0.
So when y is equal to 1, what are we getting? Our hypothesis function is log h of theta x. That's what is mentioned here. For y equal to 1, the hypothesis function is minus log of h of theta x. Similarly, you can check for when y equal to 0. When y equal to 0, the first term becomes 0, right? Correct. And for the second term, we will get minus, this is what is 1 minus 0 is 1 into log of 1 minus h of theta x, which is minus log of 1 minus h of theta x for y equal to 0. So you can say two different equations we have combined into one by introducing this new variable y, which is a class, the actual class label. And then we are iterating over all the training example. You're applying this cost function to all the training examples. So it's a summation, and then we are taking the average. So it's minus 1 by m. This is the cross entropy, binary cross entropy function. So now we have defined the cost function, and when we combine the y equal to 1 and y equal to 0, both the class, the shape of this function will look like you can say something like this. What is the advantage of this shape?
We can predict minimal cost.
Is converted.
Yeah. It is a convex, right? So when it is a convex cost function, how can we learn this parameter for any kind of a convex cost function? In linear regression cost function, was it convex? Is it convex, the linear regression?
Yes.
Yes.
Gradient descent.
So gradient descent, correct. So here we have used a cross entropy cost function, which is a convex in nature. So we can use a gradient descent algorithm to learn the parameters. So concept is not changing. What is our goal? We have defined the cost function, because once we have learned the hypothesis function, we have to learn the model parameters. To learn the model parameters, we have to use some optimization algorithm. For that, first define the cost function. So the cost function is a cross entropy function here, not the mean square error. So our goal is to minimize this cost function with respect to theta. And the nature of this cost function is a convex in nature. That means we can use the gradient descent algorithm. For each parameter, we have a weight update rule, parameter update rule. New value of the model weights are old value minus learning rate, and then take a partial derivative of cost function with respect to each parameters. And then the derivation I think I have added at the end. How are we getting finally? So derivative of this cost function, if you see, it is coming out to be this function when I take partial derivative for each with respect to each parameter, predicted value minus actual value multiplied by the corresponding feature value. Does this equation again ring any bell? You can learn and you can see, take a partial derivative of this equation with respect to every theta and see it will be reduced to this partial derivative. The second term over here will be reduced to this equation. What is the similarity? What do you see here? You have already seen this equation before.
Root mean square
Same
without
equation.
squares.
Same, it's the same equation what we see in a weight update rule of linear regression. It's the same equation.
Yeah.
So you can say the gradient rule for both the linear and logistic regression is same. The model parameter learning method is same. Theta j is, new, theta is old theta minus learning rate. And then we have this hypothesis function, we iterating through all the training example. It is predicted minus actual multiplied by the corresponding feature value. The same thing here also. For logistic regression also, we are getting the same weight update rule. What is the different here?
Here we use sigmoid function to avoid
Yeah.
the non
Cost function.
No cost function. This is a hypothesis function.
Hypothesis one.
This is different in both the cases. So what will happen? We will calculate the hypothesis function and then we use that in the gradient update rule. So from the parameter learning point, nothing is changing. We are using a gradient descent algorithm. Still, the entire theory of gradient descent algorithm, the intuition of this will work here as well, because our cost function is a convex in nature. That's what is required irrespective of whatever is our hypothesis function. Our cost function is coming out to be convex, so we can use a gradient descent learning algorithm and our life is much simpler. So this is what is a gradient descent for logistic regression. Now you know what is a gradient descent algorithm, so that will be useful. Yeah, I'm not going to talk about gradient descent here. Any doubt? Now we are done with the logistic regression. Now I'll explain what is multi-class classification. How can we solve a multi-class classification problem using logistic regression? Okay, so I can go ahead, right?
Ma'am, I have one doubt here.
Hmm.
What is the general value of alpha? That means, I think, learning rate.
Learning rate.
Yeah, what is the general value when we use or create a algorithm or model?
It is generally taken as a 0.1, 0.5, 0.01. You have to do again, this is a hyperparameter. So you can try with that.
Okay, and based on that, I need to check the accuracy or precision, correct?
Yeah, then you have to keep on changing that value.
Okay, thank you very much.
Okay, so logistic regression can only give a linear decision boundary. I mean, you can say it's a error function, and a hypothesis function can give us can only differentiate between two classes. Now, suppose if we have multi-class classification problem, and I want to use a logistic regression. So we have, say, this is a rather than cold and flu, I also want to have classification as not ill. Person is not ill, or severity of illness, level 1, 2, 3, 4, or weather is sunny, cloudy, rain, and so. So there are so many applications where we need a multi-class discrimination. So a multi-class will look something like this. So we have class 1, class 2, and class 3. So that's a hack, how we can use it. We can use this hypothesis function, our logistic regression classifier for each class, and find the class probability. And then whichever class has got the highest probability, will pick that class for that data point. Say example here. Okay, this is class 1, class 2, and class 3. For each of the class, we will find this posterior probability. So this is y equal to 1, given the features and the parameters. We will also find this is the class 2, given the features and the parameters. We will also find for the class 3. How many classes we have, we can do this. So you can say, when we do it for the, say, class 1, we'll consider the other two class as a single class. And we'll convert this multi-class problem to a binary classification problem, and then we will get a decision boundary. So it is one versus all, one class versus all. So say this hypothesis function will give me probability of, say, I'll write down, say, 0.6. Then I will repeat this for the second class. So now this is the second versus all. Rest of the classes, I'll get a probability of, say, 0.2. And then say we got this third class. So it's third class versus all, rest all. That probably I'll get, say, 0.2. And then I'll pick up the maximum number. So the maximum is a 0.6 probability that is outputted by the hypothesis 1. And hypothesis 1 is identifying the class 1 probability. Hypothesis 2 is identifying a class 2 probability. So it's identifying class 1 probability. So the answer to this, this data point will be classified as a class 1. This way we can solve this multi-class problem using logistic regression. So what we have learned, when we have to understand what is important. What is the hypothesis function? What is a model? For a logistic regression, it is 1 upon 1 plus e raised to minus theta transpose x. This is a sigmoid function. How do we interpret the sigmoid function? Is a probability of a class 1. Whatever number that we get, 0.7, 0.8, etc. It's a class 1 probability. Then we have defined the cost function, which is a cross entropy function. And then learning, we use a gradient descent because a cross entropy is a convex function. And then during the inference, like when we want to predict to the unseen data during a testing time or when we deploy in the real world scenario, total unseen data, we apply this hypothesis function. Now, X test is your unknown data point, unknown the features whose class label is not known. What theta we will use over here? Rest of the things is nothing variable. Only theta is a variable. Yes, what theta we will use here?
The final hypotheta.
So after the learning, during the training, after the final iteration of gradient descent, we are getting all these theta values, right? New theta values. After the final iteration, whatever these theta values we are learning, it is stored. And those stored theta values are used during the testing time, during the prediction of unseen data point, like that. So every machine learning algorithm, every deep learning algorithm, what happens during the training? During the training, we learn the best values of these thetas. Because we don't know the best values are 1, 5, 10, 1000. We don't know that. So during the training helps us to learn those best values of parameters, and they are stored. So when I say the model is stored, what is actually stored? This parameter values are stored. And then when we have to make an inference, we can directly use the stored parameters and then make the inference. So training is a very computer intensive, computer resource or a computationally intensive task, which takes a lot of computational resources and time. But once the training is done, when you are going to deploy the model in your application or integrated with any of the e-commerce website or any portal, what is needed is just you have to deploy the code, this code of inference code, where the theta values you will be getting during the training, what you have finalized, you are getting that. And the test is you are asking user to input this point. And your application will make the predictions. So you can imagine that you're making you have a web portal of housing price, real estate web portal, where you want to add one feature. That customer will add all the features what customer wants, how many number of bedrooms, how many square feet, and what is the area, pin code, etc. You can define what all features are good enough, and then your model, your web portal, real estate web portal will predict that if you need this kind of a house will cost so much. Just an example how we can use this ML models, AI model. Now it's a simple ML model or any deep learning based model which is used for a classification task or a prediction. Housing price is a regression problem. But if I want to classify, like I'll ask cat a dog picture or a handwritten classification. 0, is it 0? Is it 2? Is it 7? Then a model, you can have an app which can predict it's 0, 2, or 7. So this is the entire classification. Okay. Now I've taken this two examples. This is sentiment analysis. This is a task. I mean, there's a text, and we have to find out what is the sentiment of this, whatever is better. So you can read, it's a hockey, there are virtually no surprises, and the writing is second rate. So why was it so enjoyable? For one thing, the cast is great, and etc. etc. Based on this, we want to find out whether there's a positive sentiment or a negative sentiment. Nowadays, we have a lot of advanced technique for sentiment analysis. So this is no more used, this kind of algorithm. But just for understanding how this logistic regression can be used for a sentiment analysis. Or in general, any machine learning algorithm. You can change logistic regression to SVM or decision tree or any other thing. What is important, our ML algorithm cannot process this text data. The current advancements of generative AI and deep learning, you must have heard a lot of buzzwords, can process this text data, unstructured data, whether it's a text, video, audio, images directly. But our ML models cannot process this unstructured data directly. So what we have to do, we have to do feature engineering. We have to construct the features. So there are feature engineering experts, or domain experts. They have to sit and define the features. So here we have defined count of possible lexicons. Lexicons are nothing but the words. So NLP term, it's a natural language processing term, but understand positive words. Say, for example, so how many positive words are there? Say X1, you can say, yeah, where is X1 here? 3. Enjoyable, nice, and great. They are the positive words. So value is 3. Count is a function. How many negative lexicons are there? Which is X2. So you can say X2 is over here. It is telling hooky. Okay, it's not hockey, it's hooky. And a second rate. So they are the negative words. So it is 2. Similarly, we can define every features are constructed like this. Okay, take a log of word count of a dog. There are 66 words in a document. Take a log. So to define this kind of features, we need some kind of domain expertise. And then now you can see we have constructed features and the corresponding values. I can have X1, X2, X3, X4, X5. We have 6 features. And then we have this is 3, 2, 1, 3, 0, and 4.90. And then we have corresponding label. So suppose I have so many such text. This is one training example. Then I have second, third, and so on. For each of the text, such features are extracted. And then supervised, we have a label. Now, suppose this is already learnt. Like in this example, we have been already given some parameter values. So how do we use this for inference? So this new text is coming and I want to identify it's a sentiment. To use this, the value, you can say these are the values which we have constructed using feature engineering. And then these are the values W into X. So W's are coming from here. Suppose we have already learned that. And then we have stored these W's and they are coming here. And then we simple perform this mathematical computation, sigmoid functions. We get 0.70 for a positive class probability and 0.30 for a negative class probability. So as per the logistic regression threshold, what will be the class? What will be the sentiment here? Yes,
Positive.
sentiment will be positive. So it is a class 1 probability. Here we are simply doing inference. Okay, we are doing prediction. We are not training. So assume this W's and B's are already learned using gradient descent algorithm. This is just another example. Now our data set is in the form of this structured data set. So we have 2 columns, 2 features, x1, x2, and then we have a label y, class label. And we have some training example, 1, 2, 3, 4, 5, 6. We have 6 training examples. And learning rate is given, alpha is given, initial weights are given. So always we have to initialize parameter with some random values. So with a logistic regression, generally 0 can be used for the initialization. Let's initialize all the W's using 0. So this is W0, W1 and W2. With each of the features, we have what W1, W2, and then we have a hypothetical W0. We have a bias term, W0. And then we have 2 features, CGPA and the IQ. So our hypothesis function we have defined. Then this is a weight update rule. Here we are showing the training. How do we update weight after one iteration of gradient descent? This is new value of theta is equal to old value of theta minus learning rate. Learning rate is given 0.3. And then iterate over all the 6 examples and take their predicted value minus actual value. The actual values are coming from here. And for each feature, you have to multiply it by, for each parameter, you have to multiply its corresponding features. So for theta, CGPA, for each of the example, you have to multiply what is its corresponding CGPA feature value. Now from where this h of theta will come, you have to calculate. Hypothesis function will be different for each training example. So here, this is the hypothesis function and we will calculate. For one training example, apply this CGPA 5.5 and IQ is 6.7 here. That's the first training example. Plug in these values and find what is the output. That will become our predicted value for first training example. Then when we have second training example is 5 and 7. Then use CGPA is 5, IQ is 7. And then calculate h of theta x. Likewise, you will calculate for 6 such values. Plug in values over here, take a summation divided by 6 and compute rest of the calculation. So again, few steps are shown here. Use it, finish it, the rest of the steps. Otherwise, you will be lost in the exam how to solve this. It's a very simple, but okay, these are 6. How do I add it? So you have to understand the equation. Then you will be able to solve such simple examples. Okay, so what is happening here? Say after first iteration, we are getting new values of theta 0, theta CGPA, theta IQ. Theta 0, theta 1 and theta 2. Theta 0 is 0.4. This has come out to be minus 0.4. This is minus 0.6. So what we have learned, 0.5, 0.5, 0.5, that was initial value. And then after first iteration, this is what we are getting. This I can say, you can check, you can calculate and verify you're getting these answers or not. After first iteration, this is what we will get. Now say we have done after certain iterations, we have done, and this is what we are getting as the final values of thetas of gradient descent. Use it for inference. So some new candidate is coming with CGPA of 5. and the IQ level of 6. Then shall we offer a job or not? So find the hypothesis function. The class prediction is coming out as class probability is coming out to be 0.31, which is less than 0.5. So we can say predicted class will be 0. That means do not offer a job. This is the inference part. And the previous one is showing how we use a gradient descent one iteration to learn the model parameters. I mean, to come with a better model parameter. Likewise, we can have second, third iteration. So when we code it, you can have 100 iterations and come up with the best parameter. So all those, how many iterations we should run. So that convergence criteria applies here as well. Okay.
Ma'am, but to get the
Then
result, how
one
we
question that I have is,
But 1 minute. Yeah. That lady is speaking, please.
Sorry. So I was saying, to get the last inference, like to get if it's predicted yes or no, how many iterations can we decide to go up to?
See, we do
Because with
iteration, 1 minute. We do iteration only during the training. Those are the gradient descent iterations. That's what I say. There are convergence criteria. That's what we discussed in the last sessions. We can have any, so number of iteration is one of the hyperparameter. You can decide 50, 100, 50, 60, 70, 100, or check the generalization error. So a lot of things, this number of iterations we have discussed till now, but that happens only during the training. Once we have learned those model parameters, we just have to plug in into this equation and get this value. There are no iterations here during the prediction.
yeah, that's correct. But that's what I was asking. During training, the number of iterations, it's
You
up to
tell me.
us, right?
No, it's not up to you. There are a lot of theory behind it, a lot of ways to decide. I have explained. Anybody remembers? They can explain. We discussed this. Nothing changes. Whatever was there in linear regression, all those things come here. Even I discuss overfitting concept also. There also I discuss about number of iterations. Yes?
small alpha, those concepts.
Sorry, I can't hear you.
Small alpha, if you have a very small alpha learning curve, learning rate, if you have it as very small values, you'll have too many learning.
That is one
I
of the
guess
convergence criteria. But I'm general telling that how many iterations. So what is the convergence criteria for the gradient descent? One thing we have discussed. I think discussed 2-3 different convergence criteria. Can you somebody remembers one and tell me that? Am I audible? Hello? Are we connected? Are we still connected?
Yes, sir, you are audible.
Okay.
Madam,
Yeah, tell me something
trying to
remember. You should, yeah, you should remember. Because the same concept is coming again and again. See, the one of the criteria is you come up with a
God
very
function, it's minimum, ma'am. I think it's global minima.
train and test error. You can check. In gradient iteration, you may want to
RMSE should
reduce.
be in the same range.
During the training, whatever error function you decide, during the testing and training, the same error function you can compare. If the training you try, suppose I have used the RMSE as a we will check the evaluation criteria and I will try to check the RMSE values for the train and test both. RMSE is for linear regression, okay? So say this is a linear regression. Try to understand from the linear regression point of view. We check this value for during training and during testing. We try to, okay, let's reduce this, reduce this as much as possible. But then in order to reduce that, our test error is increasing and the train error is reducing. Then you have to come up with a point where we don't want to why I also explained this thing. When a train error is reducing, but the test error is increasing, what does it call?
Overfitting.
Overfitting. So that's one of the
Overfit.
criteria. Convergence criteria, you check your train and test performance and see the same evaluation metric you can use it. Whether it's a classification, we have a different evaluation metrics. For a regression, we have so many other evaluation metrics. Check the same evaluation metric value simultaneously for every iteration and then decide should you end it over here or not. If you see the test is increasing, train is decreasing, train error is increasing, but test error is increasing, you may want to stop over there. That's one of the way of looking at the convergence, or just come up with a hard number. Let's run it for 50 iterations. Let's run it 100 iterations, or just see that you run it for as many as iteration and observe every iteration that your errors, our train errors are not decreasing or decreasing with a very minute number, very small number. You stop the iterations. So many ways of this, right? We discussed this. So I cannot say just one criteria that fits. There are many different ways of looking at this convergence. It's very important to understand when should I stop the training? What should be my convergence criteria?
Ma'am, but that things we need to do in model creation, but in exam, what?
Exam we will mention.
Okay.
1 iteration, 2 iteration.
Okay.
Exam will not give you
Okay.
this job.
Yeah.
Yeah.
Thank you, ma'am.
Okay,
My
overfitting.
question was, sorry, my question here was, what happens if the probability is 0.5 exactly? How do we classify it?
That 50%. Make a decision. So it is say the hypothesis function says greater than or equal to 0.5. So our mathematically this is a function. So it will classify as what? 1. But you want to make a decision, it's a 50%, you make a decision. Model will classify it as 1. But with a 50% probability.
Or else we need to go to more iterations.
One question, in case of multi-class problems, like in binary we have 0.5, in case of multi-class also we kind of logically made it 1 versus rest. But there will be multiple ranges like 0.2, 6 and 4 be identified to classify.
So we will pick the highest probability and then we'll do the classification.
But for each class there will be a separate value or a boundary, right?
What we are doing is, see, we do that. See how we are doing this 1 versus rest. There are 3 classes. 3 classes, 3 different boundaries. But our logistic regression cannot have understand 3 boundaries. So we have done this 1 versus all. For class 1, we get 1 probability. For class 2, we are getting another probability. For class 3, we are getting another probability. Now, what should we do? Should I make it class 1, classify as a class 1, class 2 or class 3? In this case, 0.6, 0.2, 0.2. Yes?
Class 1.
Class 1.
Highest probability.
That's all. They are the same model. But one, I mean, I can say different model, yes. But the first model, we are focusing on class 1. Second model, we are focusing on class 2. And third model, we are learning the class 3. And then checking which one is the highest one. Then we'll pick up that as the classification label, prediction label.
So the total would always be 1, madam, for multi-class.
Yes. Okay, now this overfitting problem. Again, we have this kind of a non-linear data set. The first one, we try to pass a linear boundary. You can see there are misclassifications. Crosses are in the other side and the triangles are on the other side. Then on the right-hand side, we are trying to find a boundary which passes through each of the data points. Then again, this is overfitting. And the middle one, when we have a very boundary, non-linear boundary, which allows some of the misclassification, but it is just a regular, it is a regular fit. The right-hand side is not allowing any misclassification, but then it's overfitting. The same concept of overfitting applies here also. That we don't want our training error to be 0. We don't want, in this case, our misclassification to be 0. Let some misclassification happen during the training so that we get a better test performance, or I can call it generalization performance. Yeah. So this such a complex decision boundary will involve a very complex hypothesis function like this, some different interaction of the features. And then that hypothesis function we plug in a cross entropy, and then we define a cost function. We try to learn the best model parameters and come up with this decision boundary. But we don't want this. So how do we control this kind of overfitting phenomena? We have seen again that thing, a regularization. So the same regularization concept is used over here as well. L1 regularization and L2 regularization. L1, L2 regularization is more popular with a logistic regression. You can see we add a term, regularization term. This is a regularization term. Same way we have added in the linear regression cost function. Same way we are adding a regularization term. In the cost function equation itself, the first term is the cross entropy cost function and the second term is a regularization term. And now you can see what are we doing in this regularization term? Again, what is this regularization term known as? What operation or what function we are doing here?
Summing the weights.
Square L2.
L2.
We are taking the L2 norm. So this is a L2 regularization. If you take just absolute values, summation of all the absolute values, then it will become L1 regularization. So same L1, L2 concept is used here also. And then again, your gradient update rule will change because in the cost function itself, we have made a changes and added the regularization term. So we will not see we will not get into the derivation of this, but the weight update rules are changed. So you can see the final update rule is coming over here. So where alpha is a learning rate and what is this lambda here? Yes. So whatever variable that we use along with the regularization term, lambda is a very commonly used symbol, but what does it call?
Scalar.
Hyper.
It's a hyperparameter, correct, but it's known as a regularization constant. It's a hyperparameter. It's a constant sign. All the constants are always a hyperparameter. Learning rate is a constant. It's a hyperparameter. And M, what is M here?
Number of training examples.
Examples. Yes. And what is the N?
Number of features.
Number of features. So, yeah. So you have to understand all these variables. What does it signify? Okay. So this is what is regularized logistic regression. So that's all for the logistic regression. So now it's very quick to understand because a lot of theory is being covered in linear regression. Here what only changes, only the hypothesis function and the cost function changes. Any doubt? So otherwise I can go ahead. Okay. Now I will talk about classification evaluation metrics. After linear regression, I discuss about the regression evaluation metrics. So whichever regression algorithm is used, the regression evaluation metrics will not change. Like what are the regression evaluation metrics we have seen in case of a regression problems?
RMSE.
So we have mean square error, root mean square error, then we have mean absolute error, mean absolute percentage error. Then we have what? R square, then adjusted R square. We have learned this with respect to linear regression, but they are the regression evaluation metric. Even we have SVM regression, we have decision tree regression, those metric won't change. Similarly, now we will see a classification metrics. There are different classification metrics, evaluation metrics. So what are those evaluation metrics? We have accuracy, then precision, recall, F1. A lot more are there, but they are the few of one very popularly used. I'll discuss. Then we have ROC curve, AUC curve, etc. A lot of other classification metrics are available. These are the popularly used. Now you tell me before I go ahead with the classification metrics, what is the use of this evaluation metrics? How do we use it? When do we use it?
To determine how the model is performing.
On a trained data or a test data?
Train data.
Trained
Data.
Okay. Anybody with a different answer? Evaluation metrics we do not use on the trained data, we use it on a test data. Trained data, we
Yes.
use a cost function. We use cost function during the training of the model on the trained data to come up with the best model parameters. Then once we have fixed those model parameters, we use those model parameters on the test data and it gives us a prediction. So say for example, I have 8,000 training examples and I have 1,000 training example on a test data. So we have used this 8,000 examples on a trained data to come up with the best values of thetas, model parameters. Then we plug in those model parameters and use the hypothesis function on the test data. And for each of these 1,000 examples, we predict it's a regression or a classification, whether it's a real number or a class label. Then whether those predictions are correct or not, we need to check that. How do we check that? Then for that, we use this evaluation metrics. So evaluation metrics is whatever model you have come up with during the training, we want to evaluate that. We cannot evaluate on the trained data itself because that model is being built on the trained data. So to evaluate the model, we use the test data, which is unseen data. The model has not seen the test data. So if a child, you can see if we are a child has, you are giving 10 pictures of a cat and dog to the child to learn cat and dog. But the same picture, if you keep on asking a child, you cannot say that a child has learned cat and dog concept. Some other feature, some other background, maybe some other picture of a cat, other cat breed or other dog breed you're showing, and the child has to identify it's a cat and dog. Then you can say that child has learned that cat and dog. The another analogy I can give is with respect to say,
Ma'am, one
yeah,
question. If we have thousand of data, okay. So when we train the models, we actually evaluate or give 0.7%, yeah, 70% to the train or 30% to evaluation. Then in 1,000 data, 700 goes for training and 300 goes for the evaluation. Is that right?
correct, correct. We call it for a testing. The better word is testing. And then on the test data, we use this evaluation metrics to find out how it is performing. In the test data, we have seen the prediction. But then we have to find out whether this predictions are correct or not. For 300, you can, even if you manually find out, okay, how many are correct, how many are wrong. But you have to give some error metric, that how much error metric is acceptable or not, how much error is acceptable or not. So like for regression, we have all this error metric, which we evaluate a model on the test data. Now, I'm not still explaining the concept of validation. We'll talk about this validation later, sometime in some different sessions. So right now, I'm only talking about train and test. Okay, so for classification, we have this, yeah.
One question. So, evaluation is for test data, right? I understand. Regularization is this because there we change the formulas also. So that is for train data, regularization techniques.
Well,
L1, L2.
I'll ask you for that. I'll ask you a question. Okay, this is a regularization. We have added a regularization function to what?
To cost function.
And cost function. Cost function is used for what purpose?
For learning.
Learning during
Training.
model training. And which data we use for model training?
Training data.
Train data.
Training
You got
data.
your answer? You got your answer?
Ma'am, one question here. If we have if we get 100% in the evaluation data, then is that the overfitting model?
No. Overfitting and overfitting you only come to know when you compare between train and test.
Then if the training data gives us 100% result, means there is no failure, then also you can't say that it is overfitting
See,
model.
train data, first of all, 100% is not possible. But say, suppose you say hypothetical case 100%. Test data 100%, that means your model is very good or you're making some mistake.
Okay.
Yeah, so first is you have to understand with respect to classification, what is the confusion matrix? It's a 2x2 table. For a binary classification, we will understand first. And then probably whenever I'll show some demonstration, next class or next to next class, I'll show all the linear and logistic regression together, where I'll also show the multi-class confusion matrix. But let's understand what is a confusion matrix with respect to binary classification, where we have here prediction, and the actual ground truth are the actual values. So ground truth is a word many times used to say what are the actual classes. So how do you read this table? When the actual class is yes, and your ML model is also predicting yes, then we call it, it's a true positive. TP is a true positive. So if your class is yes, the actual class is yes, but the ML model is predicting no, then it's a false negative. Similarly, when the class is no, the actual class is no, and your model is predicting as a positive, it's a false positive, and actual class is no, and if the model is also predicting no, then it is true negative. Now from true positive, true negative, false negative, false positive, which out of this 4 cell, which number problematic number? There are some numbers will come A, B, C, D. So what we do with each training example, we count. Say I have 1,000 example in a test data, and then we find out the number of true positive, false negative, true negative. All these numbers we found and put in this cell. So tell me which number is you see it's alarming. Which number you should look for?
FN and
False
SP.
negative and false
False
negative.
negative and false
Positive
positive.
and false
B
negative.
and C.
No, true positive are no, which numbers you will not like if those numbers are high.
B.
False
B and
negative and false positive.
Positive. These are the 2 numbers we don't want it. But
B
there's a
and
lot
C.
more, there are a lot more general theory. If there are mistakes, if we get some numbers everywhere, which mistakes are worse than the other mistakes? So we see in ideal scenario, world scenario, we won't get a very perfectly balanced confusion matrix. So there are mistakes, you have to decide which mistakes are you are ready to accept, which you cannot accept. Based on that, you will pick the model. So assume you have many models you have developed, and then you are evaluating before you put into the deployment which model I should choose. So this is a classification. Let's understand from a classification. So use this confusion matrix, this numbers, what we put in ABCD, to have lot of numbers. I mean, lot of measures are based on this numbers. So first one is very simple, accuracy. The first one is accuracy, number of correct predictions, and total number of predictions. So the formula, very simple formula. And with respect to this true, positive, false, negative, you can see this other formula. TP plus TN. You can take some time, and there's a very logical understanding of why this formula makes sense. Out of all the predictions, how many are correct? That's accuracy. Error. Out of all the predictions, how many are wrong predictions? So this way you can find out the accuracy of the model. So generally the intuition says that accuracy is a good measure. Out of say out of 1,000, our 700 predictions are coming out to be correct. That means my accuracy is 70%. Or I can say 900 predictions are coming correct. So means accuracy is 90%. So very simplest evaluation metric is accuracy, but it has got a problem. So what is the problem? Say I have a class imbalance. So what is this class imbalance? The name, this literal word, imbalance, class imbalance. In English,
Output misbalance.
in
Maybe
our
the
training.
training
Training
data
data
is
Some
not
instances in
balanced.
class are greater than the other one.
Yeah, correct. So we have say class 0 and class 1, some of the instances are more.
Yeah.
Say class no examples are 990 in your test data set and class yes examples are only 10. So it's highly class imbalanced scenario. And in that case, suppose I get this kind of a confusion matrix. So true positive is 0, false positive is also 0. That means true, okay, true negative is 9 and this false negative is 10. These two are small number and true negative is correct. So this is what, okay, I've got a very high true negative. Now, if we calculate as per the formula accuracy, we'll get 99%. Will you accept this model?
No.
It totally depends upon what is your problem statement. Again, yes, of course, accuracy is not a good measure for a class imbalance problem, but specifically, if we are trying to find out frauds, intrusions, defects, or a cancer prediction, we know this, the example itself it would be very less. When we have credit card transaction fraudulent system, we want to predict. In 1,000 transaction, hardly there would be 1% or 2% available. We will find that data where the credit card default or a fraud would have happened. So these are the examples where we cannot balance the data set. By default, the nature of this, the problem is such that one of the class will have a very low examples. So in that case, our accuracy is not the good measure to find out because here see true positive. Say I want to concentrate more on the intrusions. I have 10 cases of intrusions and my model is predicting all 10 as a 0. I have just 10 and my focus is on to predict the intrusions, frauds. So this is not a good measure. Again, you can just read. I'll give you 2 minutes to read the slide. And you will tell me which model is better. Yes, anybody, which model you would accept this?
Both are not good, ma'am.
But you don't have a choice. You have to accept one of this. I'm just asking a relative comparison.
Ma'am, the model 2.
Model.
Yes, ma'am, the model.
Just a relative
Yes, model
comparison.
two.
Obviously, both model are not good because of the problems. So what is the issue with model 1? Even accuracy is 99%, you will not accept it because your minority class all are being predicted wrong. So that is not you want. In this case, I may accept the model even though accuracy is 50%. Now, depending upon what is my application, all my minority class are predicted correctly. Along with that, I have so many false positive. So I give an example, let's say disease example or say fraud transaction example. You have I do not want to leave out any fraudulent transaction, even though I get many false positives. What do you mean by false positives? The transaction which are not fraudulent being tagged as a fault, being predicted as a fault transaction. I'm okay, but I don't want to leave out any of the uh, fraudulent transaction, or I don't want to leave out anybody having the cancer as the, I know. So say 10 people having a disease. Out of this, we have 500 false people have been identified as a cancer. Again, I'm telling you, it totally depends upon your objective. So here I don't want to leave out any positives. So I can say that, okay, in this model, I'm not, all the positives have been identified correctly. So I will consider this model. I'll go ahead. Obviously, accuracy is low because I've got so many false alarms. That is not acceptable. But I said you have no
Ma'am, for
choice.
cancer detection,
Yeah.
for cancer detection, is model 2 good?
So I can say cancer prediction, both the models are not good in that case. Because in the first model, even the accuracy is high, the 10 patients which are actually having cancer is being left out. So that is dangerously bad. And in second model, the people have not having cancer, 500 people not having cancer is being diagnosed, being predicted as having cancer. Again, that is not acceptable psychologically to those 500 people, right? So person has to again go for a second screening, third screening. So medical domain is a very, very niche domain where a lot of general theory doesn't apply. But yeah, but I just want to say I'm a shoplifter and I just want to pick up certain artifacts, but there are only those valuable artifacts, only 10. But I want to make sure I want to pick up all the 10 artifacts. I don't mind that the 500 extra artifacts are being picked up. I don't mind that. But I'm going to make sure that I've picked up all 10 diamonds. So in that case, I can go ahead with this second model.
Got it.
So then we have certain alternative measures to deal with this kind of problem. We have precision recall. This is a formula for the precision and the recall. So what is the precision? We have true positive upon TP plus FP. That means out of all the examples which are labeled positive, how many are actually correct? So what is the precision? As the name says, precision. How much is your prediction is precise? And in recall, out of all the actual which are positive, how many have been predicted as the positive? So this is the, and you can say in the denominator, we have TP and false negative both. They are positive. The false negative and the true positive both are actually positive. Now, I've written a lot of theory. The important part, how will you differentiate when to use precision? Again, I'll take example. Book recommender system. You don't want to annoy your customers. Like you have we have a Amazon, say for example, Amazon is recommending books. Now we don't want to recommend 100 books to the customer. Out of 100, only 10 is actually false, true positive. The 10 is what your customer will like. Rest of the 90 your customer will not like. So my focus should be that I want to be very precise on what I recommend to my customer, even if some of the good books are left out. Because I know that a customer doesn't have time to go through all the 100 books. So let me have just 10, whichever book I'm giving, they should be of very high value. My recommender system should have very high value, whether it's a book or any recommendation system. Then I may look for high precision system, modern. Safe video recommendation. Again, when we have a video recommendation system for kids, it's okay. Some of the good videos are left out. But whatever our system is recommending videos to the kids, we don't want the unsafe videos being recommended. So we want very precise output. So that's called precision. I mean, we would be interested into precision, highly precise model compared to recall. So again, I gave this shoplifters example. What is shoplifter would want? To gather as much as possible, even if some of the not valuable artifacts are coming into in the bag. So in that case, he would be interested into recall, or we can say that candidate hiring. Now, when the HR system is, integrating AI, and it's okay to get the resumes or shortlist the resumes of the people who may not be appropriate, but the HR doesn't want to leave out any potential candidate. If that is objective, then it should look for the model which has got high recall. So likewise, you have to understand what is your objective and take precision value, which you should take precision value or the recall value. Recall sometimes also known as a sensitivity or a true positive rate, the other name, because you can say it is how sensitive is your system. And then when I say recall of 1, that means no false negatives. The precision of 1, that means no false positives. This way, there is no single answer, which is good. Precision is good or recall is good. Then we have another recall is sometimes, as I said, known as sensitivity and true positive rate. There's something we call true negative rate. Out of all the negatives, true negative and false negative, how many are actually negative? So that is a specificity. Again, we have to compare whether you're interested in a sensitivity, which is a recall, or a specificity. Which question you are answering? The ability to test to correctly identify patients with a disease. So you want to identify patients with a disease, even if some of the patients not having disease is getting identified. If you're okay with that, go with the sensitivity, or your focus is at the negative class. That I want to say COVID scenario, COVID screening. On the airport, what is the focus? That when the test results are coming, the focus is to classify people without disease, so that some action can be taken. They would be allowed to go. They would not require any quarantine. So our objective is to identify those cases accurately. In that case, we will be interested into specificity and this formula. And so as I said, specificity is another evaluation metric. Then we have something called F1 measure, which is the balance of precision and recall. Because if we look for a high precision, the recall is down. If we look for high recall, precision will be down. But I want to have a balance of precision and recall. So we have another measure called F1 measure, and this is a formula for F1 measure. In different terms, I've written this formula over here. High F1 measure will be good, specifically, especially when we have a class unbalance problems. So F1 will be high when recall and precision both will be high. And F1 score of 1, that means there is a perfect precision and perfect recall. That's another measure. Okay, now you can just read this slide and tell me which model is better. And I've written some comment here. But before that, you can just look at the numbers and the confusion metrics and try to understand which you should pick.
The first one.
Okay, so now we have what precision is 0.5, recall is 1. Okay, then F measure is 0.62 and accuracy is 0.9. Okay, accuracy is good in both the cases. Even if you see here, we have say true positive is 10 and false positive 10 and true negative. And here true positive is just 1. But still accuracy is good. So anyway, it's a class unbalance problem. Then second thing, when we look at here, the precision is 1. Second model precision is 1. First model recall is 1. Second, but the F1 measure is low. So of course you will, because by looking at the F1 relative comparison, you will choose the first model. But let's just understand this from a different perspective. Same problem. Say cancer prediction. Your objective is mentioned. Want to make sure that all people with a cancer will be caught. Cancer or all the people with a disease will be caught. You don't want to leave any people having disease. You don't want to leave any people having COVID. So because otherwise you are at some screening gate and you are interested into some precision. So some of the people having COVID, they will be allowed to go ahead and they'll spread it further. So if your objective is such that, then in the first you will use this recall measure. Same problem. Okay, you want to you want to confidently say that a person is having a cancer or a person is having a COVID. Then in that case, you will be interested into getting more, you will pick a model having higher precision. But here, I may not use the second model because the recall is very low. And we may want to go back and retrain the model and look for another model because F1 measure is very, very low. So that's another perspective. Same, even use a spam email classification problem. I've put the same numbers. Numbers are not changed. But now my objective is I want to make sure all spam emails are filtered. But some of the non-spam emails are filtered. I'm okay with it. Yeah, but you may not want it. But yeah, I'm okay with some of the non-spammers getting filtered. I don't want to get annoyed with the spam emails. So I will use a recall. But with a precision, I want to confidently say that this is a spam email. I don't want any non-spam email to be tagged as a spam. So in that case, I'll be interested into precision. Same problem, depending upon your objective, you'll be interested in recall and precision. So all of this measure, yeah, you can look at the F1 square if you do not understand, if you do not have a domain knowledge, or you are not very clear with which question you are answering. during the prediction, then you may look at this F1 score and come up with choose a model which has got the high F1 score. Take this without understanding the questions, domain, etc. Okay, now maybe I have 3 different model. Then I'll stop. 3 different slides. Low skew. Low skew, that means there is a low class imbalance. This is a low class imbalance. I have 100 for a yes class and I have 100 for a no class. And my true positive is 50 and the true negative is 99. And then we have got certain number. We have used these numbers and calculated. Precision is 0.98, recall is 0.5, and F1 is, okay, just look at the F1, 0.66, 0.94, and 0.99. We do not know the domain. What is this domain? So we can pick up the highest F1 score. And when we look at the highest F1 score, just look at, for that highest F1 score, we have got precision also high, recall also high. Compare the first model where precision is 98, good, but the recall is low, which is 0.5. This is a low skew case. Now when we have this medium skew case, so I have say 100 of class yes example, and for class no examples, I have 1000, the actual class. In all of this 3 models, this is what is the case. Both class examples are not balanced. And when we look at the F1 score, 0.62, 0.66, 0.94, still we'll pick up this model of 0.94, where I get precision recall both comparatively good compared to other 2 models. And when I look at the confusion metrics, true positive are 99 and false positive are 10. Okay, I'm not leaving out minority class examples so many, like just false positive 10. Compared to the second one, where my false positive are also, it's a bigger number. And the first one, again, I have true positive rate is, again, it's a low number. So you can say this, the intuition that we are trying to understand, that I don't want to leave out the minority class, which is a positive class. F1 measure can help us to identify the correct model with whatever we have. Whether even that is acceptable or not, you have to decide. False positive is 10. Can you accept that? It's a cancer prediction problem. I don't want cancer prediction problem. I may accept that false positive. But I want to make sure my maximum true positives are out of 100. 99 true positives are correct, are being captured. I may be okay with that. And high skew. So you can say this is 100 and this is 10,000. So one class example are just 100, other class examples are 10,000 in all of these models. But still you can say F1 measure is a good indicator for a model comparison. Whether this 0.6 is acceptable to you, that you have to decide. But you can rely on this measure when we have a very class imbalance, low class imbalance, medium class imbalance, or a high class imbalance. In any of the cases, you can take F1 for a model comparison. Whether to accept or not accept, that you have to decide based on which question you are answering. So here I'm ending all this discussion about confusion metrics, precision, recall, F1 score, and accuracy. And the rest of the ROC, AUC, I'll discuss next class. Okay, so, and then we will done with this classifier evaluation metric. And I'll start with the next algorithm, which is nearest neighbor. So next class, I'll start with that. And probably I'll take before the mid-semester, I will take one class where I'll show all the demonstration together, all of the algorithms together. And because the webinar also would have been done, we will get an idea. Then, so we'll take some less time in the class.
And
Yeah.
will we also have any webinar where we'll do lots of numericals,
No.
the kind of stuff that will come in the exam?
No,
for
webinars.
practice?
No, webinar are focused on implementation, programming.
But
So they
ma'am,
will help
can
you in
you make
assignment.
at least one webinar which will consolidate everything?
See, that webinar, what I can take is we can do a revision class, whatever we have done. Then in the last class, you can ask me your doubts, but please come, study and come. Before the exam, on weekdays, I can take one doubt solving session because I think you have exam on which day? Third week of Jan, right? Third weekend of Jan, you have exam.
18th and 19th, yeah.
Yeah, so before that, on weekdays, I can take, but you have to study and come. It should not be like, I have to repeat everything again. But if you want to go through, you have a recorded classes. Anything you don't want, you can go through it.
We'll do the preparation and we can do, like solve examples or whatever during the class.
Yeah, those examples. We don't have any such problem bank, but what we can do, we will do last class. I'll also discuss the last semester paper. What
Yes,
we have
ma'am.
given. Yeah, that I will do last. That paper also would be uploaded.
I mean, what kind of questions we can expect? Would we
Yeah, ma'am, like if we can do something now, so because for us, if we do at last, to
So-
retain everything also is a big problem.
Yeah, so what I can suggest is whatever problems we are giving you in every slide, do that with right from beginning to end without looking at the slide. Do that.
Yeah,
That
that
will
we
help.
will do and come
That will
prepared.
help. That will help. And concept. Today only I asked gradient descent convergence criteria. None of you could answer that. I had discussed this in last. So there are concepts that will be introduced in these questions. Sometimes the reasoning also, see the questions in closed book specifically do expect some reasoning questions where your conceptual understanding will be checked. So that's what I meant by you may not have time now, but please come do prepare before the exam. So that I can take any weekdays, I can take that class and whoever wants to join can join and ask the doubts.
Okay.
Yeah, so by that time you will also have an idea of what is the last semester's question paper, what kind of questions can come.
Yes.
Okay, so I'll continue this from the next class onwards, whatever is remained now. Anything else? Any other question?
And we have more on our plate than we can chew. So
Sorry, I didn't get you.
I said we have more on our plate than we can chew. So
Yes,
Yeah.
it is going to be like that. Especially with machine learning course, it is going to be like that.
Mhm.
Lot of concepts you are learning. These are the general concepts. So even if you learn deep neural network, the classification matrix will not change. Overfitting concept will not change. Regularization concept will not change. But you have to learn all of this along with the machine learning because that applies here as well. So next semester would be a little bit easier and not like this.
Okay.
Yeah.
Okay, ma'am. Thank you.
Okay, thank you.
Thank you. Thank you, ma'am.
Thank you, ma'am.